This project looks at developing a design perspective for understanding the notions of growth. It exposes and unfolds growth's common factors using modeling techniques frequently found in design practices. This presentation follows our empirical design research, articulating our findings through operative and open models, questioning traditional boundaries of knowledge production and transfer through design methodology. Framed in this context, our project was triggered by these questions. Is it possible to make a significant connection about growth from three different phenomena? Is it possible to find common characteristics that make something develop its form? And what are the common elements of growth, whether it be material, abstract, or living? This dynamic sketch shows our proposed common factors of growth: bonds, voids, and how density grows over time, going from simple to complex. To develop a greater understanding of growth, we materialized models that manifest this process from a shifting linear entity to a spatial structure. Studying these three apparently unrelated notions of growth, inadvertent relations were explored through debates and collaborative sketching. Here, the factors bonds, voids, density, and time were first observed as common elements between each case study. The project followed a recursive design process and was constituted by the following stages: empirical observation, experimentation, sketching, and modeling. These were some of the different linear materials that we tried together with the bond pieces designed in each iteration of the process. The design piece for the bond was fundamental for the model structuring process. Here we present the current iteration: a two-layer bidimensional piece that, when folded, creates a 3D surface to encase the magnet. The structure of the piece resembles the properties of the larger structure, creating bonds and voids. The bond piece creates a space in which the magnet can rotate, allowing it to change its form, from that of attention to attraction, when the two pieces are in close proximity. Through playful experimentation, we built and reset models over numerous iterations, intuitively learning the behavior of form on various scales. The categorization of behavior permits us to transfer our knowledge to scientific models, algorithms, and material properties. We were able to match discrete forms found within the growing structure with particular behaviors of the model. This is an example of some of the discrete forms we were able to define. This recipe is the simplified documentation of a standard algorithm we commonly used to assemble our models. The project will continue in the future by coding variables found in this growing process, comparing them to existing parametric models. We invite you to share your thoughts and comment on our understanding of growth. We encourage changes to both the model's material elements and methods of construction. This open source design is collaborative, and we encourage people to improve upon the source model and share the changes.